Hello, everyone, and thank you so much for joining us today. I hope all of you are doing great. I'll start off by introducing myself. My name is Ahmed Gamal. I'm a graduate student at Cairo University and the PERW Committee Chair. And I'm very happy to be here today, host, alongside the PERW Committee Chair, Kelly Hughes from Virginia Tech University. Today's webinar is hosted by the SLC PERW Committee. The PERW is part of the SLC that is responsible for hosting a post-earthquake reconnaissance workshop. The workshop aims to help the students to learn more about earthquake damage and damage assessment, and also is to give them a hands-on experience on how to make damage assessment themselves in the workshop. This year, we decided to help the team that are participating in the seismic design competition with their fourth and last deliverable, hoping that all of you guys have done a great job with the Path 3 ones. Before I go ahead and tell you more about what else the PERW is hosting for you, I would like to thank our today's speaker, Bill Tremayne, for accepting our invitation, and all of the SLC members for making this happen. Also, I would like to mention that we are joined by a couple of people from outside the competition, so thank you for joining us as well. Besides today's webinar, we are hosting a workshop on Monday, April 19th, about the last year 7.0 magnitude earthquake that happened to strike the city of Izmir in Turkey and part of the Greek island. We're going to have very prominent speakers to tell us about their post-earthquake reconnaissance experience working in both countries, Greece and Turkey. Also, we're going to learn more about how to make damage assessment of collapsed buildings after an earthquake. And I guess some of you guys will be graduating this year, so we're going to have a talk also on how to stay connected with EERI after graduation. It's going to be very beneficial and informative workshop for everyone to attend. So it's highly recommended for you guys to look at it. All information about this workshop can be found on our social media platform. Please take a look at it, and we're looking forward to seeing you there as well. Now we'll pass to Kelly, and she's going to tell us more about today's webinar.
Great, thanks, Ahmed. So I'm very pleased to welcome Bill Tremayne here to talk to you all about seismic retrofitting. Just some logistical items before we get started. Please, if you have any questions as the talk goes on, you can go ahead and type them in the chat box, and at the end we'll kind of go through them in order. If you would like to ask the question yourself, you're more than welcome to. Again, at the end of the presentation, we'll let you unmute. Or if you would like me to read the question to Bill, I can also do that. But if you would please put them in the chat so we can keep track of where the questions are coming from and who's asking them, that would be great. Other than that, please keep yourself muted throughout the presentation. There are a lot of us in this room, so we're going to let Bill talk the whole time until he gets to the end. So again, save your questions for the end. Okay, so with that, again, I'm pleased to welcome Bill Tremayne. He is a principal and technical director with Holmes Structures in San Francisco, California. He has over 19 years of experience, and his areas of expertise include nonlinear analysis, seismic retrofit of existing structures, and new commercial construction. He's a strong proponent of performance-based engineering and serves on the main committee of ASCE 41, in addition to chairing the masonry subcommittee. Bill is also a regular contributor to FEMA and other industry-funded research projects to bring next-generation seismic design guidance into practice. So thank you, Bill, and we will pass over the screen sharing to you.
Great, thanks, Kelly. I will pull up my slides. Okay, move this out of the way. Is everything looking good on your end, Kaylee?
Yep, looks great.
Perfect. Well, good morning, everyone from Oakland in California. I'm really happy to be here and happy to have accepted this invitation to present to you all about seismic retrofit in a design office setting, and hopefully share some of my experience and our firm's experience with approach to seismic retrofit practice, sharing some of the philosophy that we have around how we approach thoughtfully evaluating and retrofitting existing buildings, understanding the framework in which we operate as practicing structural engineers from a code and design standard perspective, and then also showing a case study of a retrofit project that's particularly near and dear to my heart. But I just want to give a quick overview of the firm that I work for. So as Kaylee mentioned, I work for a firm called Holmes Structures. I'm based in San Francisco. The background here is our office at the moment. We unfortunately don't have anyone in person in the office at the moment, but I like to be reminded of what the office setting was like a little over a year ago. But Holmes Structures is part of we're a structural engineering practice, but we're part of a multi-specialist engineering business called Holmes Group. And we provide structural and fire engineering design services on both sides of the Pacific, between New Zealand, Australia, the US, and also a little further afield in the Netherlands. We also have a product development and testing group as well. And one of the things that knits all of these different parts of our business together is a real advocacy and a passion for using performance-based and evidence-based design in how we deliver complex new buildings, and also with seismic retrofit. We've found that the performance-based framework is, which I'll be talking a little bit more about throughout this presentation, is the best way that we have available to go about evaluating and thoughtfully retrofitting existing structures. And this is just for a bit of context. This is the group of folks that we have spread across some of our West Coast offices back when we were all together over a year ago, and I haven't seen many of these folks in person for a while, but we've been doing a lot of interaction like this, and it's been working out reasonably well. But certainly looking forward to seeing everyone in person sometime soon, hopefully. So just an overview of what I'll be going through, as I touched on earlier. I'm going to start with an overview of, or an introduction to, seismic retrofit approaches that we use in our practice, and more generally as practicing structural engineers in high seismic regions. Talk a little bit about building codes and standards, some of the terminology around seismic performance definitions, retrofit triggers that we commonly encounter as practicing structural engineers working with clients and with building departments and cities, and understanding what the needs are around why a retrofit might be triggered. Talk about retrofit objectives, and then I'll give an overview of common systems that are employed in retrofits, depending on the structural system of the existing building. And then I will finish up with a case study of a high-rise seismic retrofit that I worked on a few years ago in downtown San Francisco. So just to set the scene in terms of the regulatory environment in which we operate as practicing structural engineers, certainly in the US, we commonly design new buildings in accordance with the International Building Code, or sometimes, depending on the state that you're in, there might be a local version of the IBC, such as in California, there's the California Building Code, which essentially follows the same format as the IBC, but has some localized amendments that are specific to the needs of the state. And so the IBC works in conjunction with a standard called ASC 7 that defines the loads and the seismic hazards and some of the other design criteria that we use to proportion and design and run through code conforming checks for new construction. And that works really well where we have a lot of this, it's almost a cookbook approach, where you look up a series of prescriptive requirements that the building is required to meet, and you proportion and design and run member checks and ensure that the building meets the drift requirements that are prescribed by the building code, and you make sure that all your demands are less than the capacities that are prescribed by the building code, using for seismic design, a single R factor that is used to divide the elastic forces and get them down to a level of load that we use for design of code conforming structures that meet all these prescriptive detailing requirements, whether it's for concrete or for steel construction or other construction types. And so this approach works really well where we have a lot of control over the variables in a new building. But it rapidly gets a lot more complicated when we start evaluating existing construction, where the materials are archaic, they may have deteriorated, and they don't conform to the requirements that are prescribed by modern building codes and reference standards like ACI 318 or the AISC reference standards for new construction, we quickly run into problems trying to apply a new building standard like the IBC and ASC 7 to successfully evaluate and determine the capacity of existing buildings, particularly when they're a mixture of different structural systems as well, which is pretty common in a lot of older buildings where they mixed and matched concrete and steel, masonry, and you have to grapple with how do you evaluate the building. There's no single R factor that can be applied to divide the forces by to go through and run a system-wide check of every single component in the building. So this is where a document like ASC 41 is hugely valuable. It's a performance-based standard. It does fit into the framework of the IBC as an alternative means of evaluating buildings. And it provides a lot more granular detail to practicing engineers as to how to go about evaluating all the different components that are commonly found in existing buildings that don't conform with modern standards. And so this is going to be, I'm going to be using this as a point of reference as I talk through some of the retrofit approaches and philosophy that we use, and also for the example building case study later on. So this diagram is just an illustrative way of looking at how a building code approach, which is just essentially a single dot on this continuum of seismic performance and earthquake intensity, how a building code approach from, say, the IBC and ASC 7 maps onto a continuum of building performance, looking at how the structure and the non-structural components perform, and the seismic hazard that we use to design for. The building code is like I said, very simple. You have a code-defined design basis earthquake that defines the hazard, and then you also have a prescribed performance objective, which is set by an R factor that's used, and it's implied that building code essentially gives life-safe performance at what they call the design basis earthquake. And that works really well for buildings that conform to all these prescriptive detailing requirements. You get stable, predictable response that meets an implied probability of collapse. Now, as I've mentioned, existing buildings often don't sit won't sit at a single point because of the mixed systems, the non-conforming systems, and we often find that existing buildings, they sit on a continuum of performance. And it depends on the specific deficiencies that we find in different components of the building. And we often find that existing buildings, when you start evaluating them, because of some of those deficiencies, they don't conform to, or they don't meet life safety, for example, at the design earthquake. They might sit, once you start looking at all the different limit states and the deficiencies, they may perform at a lower level of, they may meet that performance objective at a lower level of shaking, or they may not meet that at all. And the analyses that we run show that the building collapses, and perhaps you would qualify that the building might meet a lower level of performance at a lower level of ground shaking intensity in the as-is condition. But this helps, having this type of a framework helps us to set the stage of understanding where the existing building sits, and perhaps if there is a retrofit that's triggered, what are we trying to achieve with that retrofit? Are we trying to lift the performance? Are we trying to lift the level of hazard at which the building meets a specific performance objective, or if it sits at collapse prevention, can we just lift the level of shaking at which it continues to meet collapse prevention if that's the performance objective that's selected or mandated by a city or a client? I also wanted to share just a little bit more framework setting. All buildings have some sort of generalized backbone or pushover curve that helps us to generalize the response of a building to a level of ground shaking. And this plot here is basically a plot of base shear, or the strength, the capacity of the building, versus the displacement capacity of the building, or ductility. And less ductile, older structures often exhibit a drop-off, a rapid drop-off in strength, because at increasing levels of displacement, sometimes this point is pinched further back when the building has certain brittle modes of failure. And so this, if we're able to run through some initial analyses that give us a picture of how the building is expected to perform, at increasing levels of input ground motion or hazard, we can start to get an understanding about where the vulnerabilities lie, where the damage may concentrate in the building, and we can then start to inform ourselves as to how we might think about retrofitting the building. Just a little bit of terminology, and I grabbed these in terms of some definitions around performance objectives or performance criteria that we commonly use in retrofit. And this draws upon definitions that are provided in ASCE 41. And these relate to the chart I showed before as well. There are 4 levels of broadly defined levels of performance that then feed into very detailed acceptance criteria and modeling parameters for components. But at a high level, there are 4 broad categories of performance that are defined: collapse prevention, life safety, and this, as I mentioned before, is analogous to the level of performance that is implied by the building code when a building code conforming building is subjected to the design basis earthquake. For higher risk category or higher occupancy structures, perhaps essential service buildings, I think I understand that the balsa wood models that you all are developing are around a hypothetical hospital. So a hospital, for example, would fit into this definition of an essential services building that serves a critical function to the community after an earthquake or major disaster. And both the building code and ASCE 41 acknowledge that by requiring more stringent design requirements. And this is reflected in ASCE 41 by requiring that at the design basis earthquake or BSE1 hazard, as it's defined in ASCE 41, that the building meets what's termed immediate occupancy. Now, there's another category as well called, which is a even higher level of performance called operational. And the main context for that, and so far I've been talking about structural performance. This is looking at how the primary structure of the building, the gravity systems, the lateral systems perform in an earthquake. The other important component, I'm going to continue touching on this as we go through the presentation, that we certainly pay a lot of attention to in our evaluation and retrofit work, and is getting increasing attention, I think, at the national level as well, in terms of the impact of non-structural performance on building resilience and functional recovery. The ASCE 41 does prescribe performance requirements as well for non-structural components. They're a little different from the requirements for structural. They don't map across directly, but there are certainly requirements for essential service facilities under this what's called position retention category of performance. And then there are also requirements which are ideal targets to achieve for an essential service facility around operational performance. And a lot of the additional criteria that kick in for operational are to do with non-structural and to do with the continued operation of energized systems, electrical, mechanical components that help keep a building running, the elevators, making sure that those components after a design earthquake continue to be operational, not just that the building is undamaged structurally, but the components and contents that help the building be an operational facility and useful to the community are actually operational as well, without having to have the maintenance teams go in and fix or correct the position of elements that may have had plugs come unattached or leaks that have occurred. So to help further set the scene, I thought it'd be worth just to touch on why retrofit. There are all kinds of triggers that can result in us getting a project where we step through an evaluation of an existing building and start to develop retrofit schemes and ultimately implement them. There are building code triggers in the IBC and also in the California Building Code, and other jurisdictions have their own requirements as well that sit on top of that. So some common triggers in the building code: changes of occupancy, increases in occupant load, additions and alterations. If you alter the structural system of the building, you may be required to reevaluate it. If you add mass or add stories or a horizontal addition to a building, there are triggers in the building code as well that require evaluation. And if you cross a certain threshold and a change in the demand capacity ratio, you need to step through a retrofit. And that would generally, certainly in our practice, we'd typically be doing that in accordance with ASC 41. If the building is damaged or needs to be repaired, there are also triggers. If the damage is substantial enough, the building may need to be retrofit. And also sometimes the seismic hazard, our understanding of the seismology of a given site changes. The ground shaking intensity for the design earthquake may increase, and that may trigger a retrofit as well. And then folding into that at the city or jurisdiction level or at a building department level, some jurisdictions around particularly on the west coast of the US, are implementing retrofit ordinances that target vulnerable types of construction, unreinforced masonry buildings, non-ductile concrete, pre-Northridge steel moment frames are just a few examples of some of the ordinances that are in place or coming up along the west coast. And then there are also voluntary retrofits as well. Our clients are interested in enhancing the safety of their buildings, improving the resilience and the ability of their buildings to be reoccupied rapidly after an earthquake. And ultimately, there's a really powerful sustainability message as well around retrofitting buildings. The most sustainable thing that I think you can do with an existing building is to retrofit it and continue using it for another 50 years rather than tearing it down and throwing all that embodied carbon back out into the environment. This image here on the right of the screen is an aerial photo of downtown Christchurch after the 2011 earthquakes. Just showing the extent. This used to be a fully built out downtown central business district that was thriving. All the bare patches here are where buildings used to be that were either severely damaged and torn down, or the red dots are also some taller structures that were slated for demolition at the time that this photo was taken, and they were ultimately torn down as well. So there was a significant, and this touches on a couple of things. There were changes in the seismic hazard that had understanding. There were a lot of unretrofitted, unreinforced masonry buildings or partially retrofitted buildings, and some interesting issues around the understanding of localized site effects that contributed to some intense ground shaking in this area that contributed to a very significant disruption over many, many years following these earthquakes because of the extent of damage and demolition that happened to the downtown area of Christchurch. So what are we trying to address with a seismic retrofit? In our practice, we really like to start out with the understanding of the existing vulnerabilities and having a comprehensive understanding about how the building is going to perform at different levels of shaking intensity, or if we're simplifying it with this backbone or pushover curve, this is just illustrative of giving us an understanding about where the building and its as-is condition sits. And we're typically looking to address one or more of these system characteristics. We're looking to add strength to the building. Perhaps we're looking to add stiffness, ductility capacity, energy dissipation, damping. We may also be looking to add stability or a restoring force to ensure that the building can be righted and centered after the earthquake. Those are rocking, restoring systems to ensure that the building doesn't have a permanent offset after a given level of shaking. And we're also looking perhaps to improve the performance of non-structural components, whether that's through changing the building response, and I'll touch on that a bit later on, or improving just the anchorage and bracing of non-structural components. And this is just illustrative of how playing with these parameters over here or characteristics of the building through a retrofit can help change the backbone curve. If we add strength and ductility, maybe we're bumping the curve up and we're also helping to push it further out and mitigate these brittle failures that contribute to a rapid drop-off in strength. Or perhaps we're adding additional ductility to the system or damping. We may also be looking to introduce a base isolation system that really cuts the demand significantly, pushing the force demands down, but giving us a nice, stable post-yield plateau that allows the building to displace further when subjected to a larger seismic hazard. So I thought it'd be good to touch on some common approaches to seismic retrofit that that are outlined in a lot more detail in ASC 41, but I'll touch on some of the ones that, and there are other systems as well beyond what I've got up here on the screen, but these are certainly approaches that we commonly use in our practice and are big proponents of. So a few common approaches for seismic retrofit: concrete or shotcrete, which is a sprayed application of concrete to form reinforced concrete shear walls in a building. Steel braced frames, buckling restrained braces have gained a huge amount of traction in the last 10 years in seismic retrofit. They've been used in new construction for a longer period of time, but we're seeing a lot of buckling restrained braces being introduced into seismic retrofits, perhaps to replace older non-conforming brace frame systems that don't have as good a ductility capacity. Special concentric brace frames are also a relatively stiff and somewhat ductile system that can be employed in a retrofit. Steel plate shear walls, a little more common in new construction, but we have seen applications of steel plate shear walls as well in retrofit solutions. They're a very compact way of retrofitting buildings where space on a floor plate is tight. Rocking and restoring frames or walls using post-tensioning systems to help provide a recentering force. And this technique can be combined with some of these other systems as well to arrive at a hybrid solution. Viscous dampers, and I'll touch on that a little bit later, and base isolation as well is kind of I guess the Cadillac solution that we would love to see more of on our retrofit projects, but it's not always the most appropriate for a number of reasons, but it certainly is one that can deliver very, very significant improvements in seismic performance for a retrofit. So in conjunction with thinking about some of the biggest system-wide pictures around retrofit systems or alternate new systems to introduce into a building, there are other considerations that need to happen in conjunction with just thinking about the retrofit approach at a system-wide level. We're always thinking about deformation compatibility. How are the new retrofit systems going to interact with the existing components in the building? Are they able to attract enough load or to control enough of the deformations to ensure that the existing components that may be part of the gravity system, making sure that they are able to continue accommodating the deformations, or that their deformations are reduced enough that they are able to continue serving their function, say as a gravity load supporting element. We need to evaluate the foundations and make sure that the new retrofit elements that we're introducing into the building don't add significant foundation loads in areas where we don't have enough capacity, or that we're strengthening the foundations as needed. Floor diaphragms, collectors, and connections are also important considerations, and addressing discontinuities as well and irregularities in the vertical load carrying system are often a localized area that we study when there are discontinuities in the building system. And then also non-structural anchorage and bracing, trying to mitigate these types of hazards, which can have consequential effects, just even if the building is undamaged structurally. So I'm going to talk a little bit in some detail about 3 different retrofit techniques that we commonly employ in our practice, and just talk about quickly touch on pros and cons. So reinforced concrete shear walls, some pros: they're relatively stiff and strong, they have good ductility capacity, and they're a relatively inexpensive form of retrofit relative to other retrofit methods that I'll touch on. Some of the cons: they tend to be heavy. They add mass to the floor plates and also to the foundations. They can be architecturally impactful. This is a concrete shear wall going in a building, and you're typically cutting off access through the floor plate, cutting off access to daylight by having solid wall elements. And you also need to introduce collectors and potentially diaphragm strengthening as well to transfer the loads around the floor plate to get them to where those shear walls are being introduced into the building. Viscous dampers. So these are a particularly effective means in relatively flexible structures in particular of reducing the demands. The nice thing to the primary building structure, the nice thing about dampers, viscous dampers, is that they have this out of phase response between with the primary lateral system of the building. So the forces that the dampers introduce are often not as additive, or if not completely out of phase with the response of the primary building structure. So they don't tend to add significantly to the column axial loads if you're engaging existing elements of the lateral system. And that's this out of phase relationship that we expect to see between velocity and displacement. They can be configured as diagonal braces, which is in this image down here, or as wall dampers, depending on the product or manufacturer that's selected. And so diagonal braces are certainly advantageous in terms of allowing path of travel, daylight coming into the building, those sorts of things. And we've found they're particularly effective at reducing base shear demands by up to 25% or more, depending on how they're configured. The dampers are replaceable, and they have this great benefit of reducing floor accelerations. And I'll share a slide on that in a second. There we go. This is just a comparison from a building that we looked at where we added viscous dampers, and this is actually a plot of floor response spectra. So we're thinking about non-structural performance on a given floor up the height of the building. And so the undamped response of the floor plate at a period of 0.6 seconds gave our peak spectral floor acceleration of well over 10 G for an essentially elastically responding steel frame building. We added the dampers, and we were able to pull those peak acceleration demands further up the building down to a much more manageable level for the design of the non-structural anchorage. A couple of cons around the use of dampers. They do require some drift to activate the stroke of the damper to get the to develop the damping force, which means that the building does need to continue displacing a reasonable amount. And so the deformation compatibility checks are very important to run through with a damper system. And they do tend to be relatively expensive in terms of the technology. Some of the dampers have a lot of proprietary technology in them, and the availability of suppliers and sourcing can be a little tricky to navigate sometimes on projects. And this is an example of what I've been talking about with non-structural, especially with essential service buildings that have a lot of mechanical investment in mechanical systems to help the buildings be functional and provide all the services that are needed. There's a lot of non-structural components and contents that need to be braced and anchored, and they need to be secured so that they don't have disproportionate consequential effects like this building here that was damaged in the Napa earthquake in 2014. A sprinkler head or a sprinkler pipe in this building burst. The building was otherwise not that badly damaged structurally, but the consequence of a sprinkler bursting in this building and flooding the building for a couple of hours until they could shut the water off resulted in a very, very expensive rebuild of the ground floor of this building, with all the non-structural finishes being torn out due to water damage. This is just an example of how we implemented the dampers on a building, high-rise building in Wellington in New Zealand. We completed this project a couple of years ago. This building was relatively flexible, but it had reasonably good strength and drift capacity, but it was overly flexible and had a pounding problem with an adjacent structure. So we introduced dampers over the full height of the building and the flexible or weak cure direction transverse. And we were able to significantly pull back the demands in the building and also mitigate this pounding hazard as well. Base isolation, as I mentioned, is seen as kind of the deluxe or the Cadillac solution for the retrofit of particularly of monumental and historic buildings, where we're really trying to minimize the amount of retrofit work that we're doing in the superstructure because of, say, the impact of the architectural program or the impact on historic finishes as well, or historic fabric. There are a number of different base isolation technologies that are available: lead rubber bearings, friction pendulum sliders, and these components introduced at the base of the building help the builder isolate the superstructure from the response of the ground by accommodating the ground motion across this isolation plane. They're self-centering, so the building returns to a zero offset after the earthquake, and the units are also replaceable if needed. Some issues to keep an eye out for with base isolation. Uplift or overturning demands can be difficult to accommodate with the isolators. They're not great at resisting tension loads. The design, certainly from a design office perspective, the design and approval process usually requires third-party peer review. So the design schedule and the design schedule needs to take that into account, and certainly that's an issue we run into in the design office when considering whether base isolation is appropriate for some projects. And there's a cost premium associated with them for a couple of different reasons. You've got to manage this moat here to ensure that services and utilities can transition from the street or at grade into the building, that people can get across the moat with architectural cover plate systems. And then there are also issues as well with transfer elevators out of basements and podiums as well, which can increase the cost of some of the services like elevators and other components that need to transition and run up the height of the building from grade level. But the big benefit from a structural perspective, as I've touched on, is you get this, that the isolation system shifts the response of the building significantly. You can shift the period from a fixed base building at say a half second out to 2 seconds, 3 seconds perhaps, and that really cuts the input ground shaking demands down significantly. And you also get the added benefit of increased damping. The isolators have significant damping capacity, 10, 20% or more damping capacity, and that helps further reduce the input demands out of that elongated period. So I thought I would share a quick case study of a retrofit that I worked on in downtown San Francisco a few years ago that was completed, particularly near and dear to my heart. It's 140 New Montgomery Street in downtown. It's actually just a little, for those of you familiar with San Francisco, it's set just south of Market Street. And I thought this would be a great way just to show an integration of a few of the different retrofit philosophies and techniques that we've touched on through the prior slides. So I'm just going to switch presentations here and pull up another PowerPoint. Bear with me. Okay, can everyone see? Kaylee, can you see that?
Yep, that looks
back
good.
in presenter mode?
Yep. Great.
Okay, I'm conscious of time, so I will keep moving here reasonably quickly. But please save questions for the end, or I can happily go back if we have time. So this is it's a registered historic landmark in downtown San Francisco, and it was completed in 1926. It was San Francisco's first skyscraper. And it was built by Pacific Telegraph or Telephone and Telegraph Company, precursor to Pac Bell, which is now part of AT&T. Just for a little bit of history there on who'd owned it and why it was built. And there's some fun photos in a minute that I'll share. And it was designed by a couple of prominent architects and engineers who helped define the skyline of San Francisco. They built a number of monumental buildings that around the city, including the structural engineer Tremayne Ronenberg designed the Legion of Honor building, which is a particularly significant building in San Francisco, as well as this 140 New Montgomery. Some images of the building going up. It's during construction, it's a riveted steel moment frame. Interesting, and I'll touch on this in a second. They were paying attention to lateral loads at the time. They designed these haunched, they called them wind gusset connections at the time, around the perimeter of the building to try to stiffen the frame and provide some inherent lateral resistance at the perimeter. And then also the building was encased, all that framing was encased in concrete, brick, and terracotta to provide fire rating resistance. But it also contributes, as we've found through the analysis that we've done, to the strength and stiffness. Some completed photos of the building in 1926. This is, so it was used as a telephone exchange building, and some beautiful historic photos of what folks used to be doing in there. But then not much changed with the building from 1926 to 2008. Kind of looks pretty much the same. Beautiful historic lobby, entry lobby that we're really pleased to have preserved as part of the retrofit. We were very fortunate to work with a great developer who purchased the building from AT&T, and they articulated this fantastic vision that really helped drive us with our selection of retrofit approach and how we approach the design and detailing as well. So some of the other conditions in the building, I don't know if people are familiar with Mad Men. This is the corridor layout in this building is very much the same as a scene out of Mad Men. I was half expecting as you walk down here to pop open one of these doors and Don Draper's sitting in there smoking a cigarette and drinking a martini or something. But yeah, pretty stagnant office layout and not conducive to the modern needs of building tenants in downtown San Francisco when we started looking at this in late 2008. The facade had fortunately had some retrofit work done to it, and then they'd also mitigated these amazing Falcon busts up at the roof of the building that help guard the building, I guess. Used to be terracotta, very fragile and brittle, but they'd replaced these with fiberglass busts back in the 80s, which was certainly helpful from a non-structural perspective. We spent a lot of time digging into understanding the existing building after they'd gutted all the finishes and interior of the building. Went through an extensive material testing program to understand the capacities and strengths of the steel, the rivets, the brick infill, so we could develop a comprehensive understanding of how the existing building would perform. This is just an illustration of the typical floor plan. It's an L-shaped floor plan. For those who've spent much time evaluating or analyzing buildings, this might jump out at you as being a building that could be torsionally irregular. It certainly was, and that was problematic to deal with. A lot of twisting action that we had to reconcile between the ends of the building versus the center of the diaphragm. Just imposed a lot of extra demand on the existing framing systems at the ends. We went through and did a lot of component studies on how the masonry facade would interact with, which contributed strength and stiffness, but not a whole lot of ductility. We wanted to see how that interacted with the steel framing. So we did a lot of sub-assembly studies. Did that for every single configuration that we could find up the height of the building because the infill systems varied. We also did some material testing and found also that the column splice details didn't always match what was on the drawings. Well, the drawings were really hard to read, so we needed to go and do investigation anyway. We went through, studied these wind brace connections that I showed on the photo earlier to gain a good understanding about how these connections were detailed, how they were built, and incorporate those into a 3D finite element model of the building. And so we went through, studied the building's performance relative to varying levels of hazard and started to identify where the weak spots were. Columns and column splices were vulnerable. The facade was vulnerable to damage because of excessive drift demands at the perimeter. And we had some areas of weak or soft stories as well developing because of some irregularities and setbacks in the building framing over the height. So there were a couple of, touching back on why we went through the retrofit. We were triggered by the San Francisco Building Code to retrofit the building because of the extent of the renovation scope. But it's a historic building, and so there were some other factors that came into play as well with how we approached the retrofit. We had to adhere to the California State Historical Building Code in this particular instance. And we employed ASC 41. And it was the 2006 version at the time, but we're now working with the 2017 edition. And the criteria that we worked with was to evaluate life safety or to design the retrofit to achieve life safety at 75% of the design earthquake or BSE1. And in conjunction with our peer reviewers, we worked through a process of providing additional protection of critical force controlled actions in the building that we all identified and agreed was important to ensure we're protected, to ensure the building had some additional robustness over just meeting the single performance objective. This is the approach that we took to thinking about how to evaluate different retrofit approaches. Now this was tailored specifically to this building, but I think you could easily apply this type of philosophy when thinking about how to approach retrofit of other building structures and other tenant needs or other drivers on a project. but it's an integrated and iterative approach. We think about constructability. We're thinking about how the retrofit minimizes the impact on or reduces the demands on the existing elements. Sometimes it's the foundations or the historic fabric as well that we're trying to protect. We're thinking about the overall cost, impact on the floor plate so that it's still a usable, functional building that can be rented out to tenants, and also similarly feeding into that the architectural layout implications as well. And we're coordinating with the architectural layout as well, as I'll show in a second. We found it helpful in our discussions with our client to have a matrix of options, and we put weighting factors on the things that were important to everyone on the team: historic impact, structural efficiency, plan integration. It was important on this project to minimize foundation impacts, overall cost, and our client wanted to know about the coolness factor as well. It was pretty important with how much we were pushing the boundaries with the solutions that we were coming up with, and coming up with something that was really outside the bounds of what would otherwise be potentially be a vanilla reinforced concrete shear wall retrofit scheme. And the solution we arrived at for this building was a reinforced concrete shear wall system with BRB outriggers. And this is just a typical floor plate again, showing where we put the reinforced concrete shear walls in red, and the blue lines, the outriggers, and I'll show those in a second. But we also added some shear walls at the ends of the building to help control torsion. This is a 3D view of the reinforced concrete shear wall system with these buckling restrained brace 2-story deep outrigger trusses that engaged a reinforced concrete encased steel super column at the perimeter of the building. And this really added a bit of everything that I've touched on before in terms of what we were using the retrofit to achieve. It added strength. We gained ductility by having this buckling restrained brace outrigger that fused and helped limit the demands that the concrete shear core and shear walls saw. We added some stability through a rocking foundation system, and also through the stabilizing effect of these outriggers that helped to introduce additional points of inflection over the height of the shear wall. And we also added collectors as well to drag the loads around the floor plate to get to these more concentrated locations of lateral load resistance. I think I'm a little short of time here, so I'm gonna, if there's time, I'm happy to play these videos later, but this is just, we simulated the response of the concrete, of the retrofit only to a suite of ground motions using a nonlinear analysis. And we're able to explicitly evaluate the performance of the new lateral system. And then we also went through and looked at deformation compatibility and considered the entire building system with the new retrofits integrated, and evaluated the performance of the building in its combined state. And there are always surprises that come out of an analysis like this. We found that the existing columns at the perimeter of the building still needed strengthening because of the induced demands from the drifts. We just weren't able to pull the drifts back far enough. And so we did some column strengthening, and we also strengthened the splices as well to ensure that the columns could develop and deliver the loads that were being induced to them and get those down to the foundations. Just some images from construction. There are always surprises that turn up when you retrofit these buildings. We had to do some connections to the existing foundations, and we quickly found out in the sub-basement that the foundations had also included these 4-inch thick milled steel base plates to these columns that were stuck on top of the basement slab. So we had to work around that pretty quickly as the contractor started to get on site and adapt our details. These are just some images of the reinforced concrete shear walls being constructed through the building, cutting out the floors, floor slabs, preserving some of the gravity framing, in between detailing the rebar and the boundary elements to pass around the existing floor framing, so we maintained the gravity load path. This is just one of the outrigger trusses up the height of the building, engaging that super column. We had a fantastic contractor on this project. They picked up these are the embedded steel super columns that they picked up with a tower crane, several stories tall, and they dropped them down through the height of the building, all the way down to the foundation level from the roof of the building, and landed them on a grout pocket on top of one of our foundation walls, and spliced all these columns together and then encased them in concrete. These are the buckling restrained braces, our yielding fuses. These are 1200 kip BRBs that Core Brace manufactured. And just some finished interior shots. Murad Restaurant was one of the anchor tenants that took over the part of the first floor. Beautiful space. The client was extremely happy. We were able to keep the strengthening away from the facade, interior facade of the building, and preserve that coolness factor that they wanted. They wanted to have modern functional office spaces that also preserved the exposed brick. That was certainly appealing to a lot of the tenants at the time when they started leasing. And that's a completed shot of the building after the facade restoration was completed, and they finished doing some wonderful upgrades to the exterior lighting as well of the building to continue showcasing this building on the downtown San Francisco skyline. So that wraps up the formal part of the presentation. I'm happy to take questions, open it up for discussion.
Great, thank you so much, Bill. That was fantastic. What a beautiful building. Really, really nice. And some really cool shots you have of that. So thank you again.
Yeah, welcome.
Again, we will open it up to questions. You can feel free to put them in the chat. Or if you would prefer to just unmute yourself, we can try that. But we're having some come in right now. So Garrett Barker, if you want to ask your question, you're welcome to unmute yourself.
Yeah, thank you for that presentation. That was awesome. I was wondering, is it possible for retrofitted buildings to be able to reach kind of a performance that can be compared to some newly constructed buildings, or is it always kind of a struggle to reach that point, and you're always going to have maybe a retrofitted building that isn't as highly performing as maybe a newly constructed building would be?
It's certainly possible to achieve, and we've done that before. It is always a discussion that you need to have with the client and the city or the permitting authority early on as to what the performance objectives are. A lot of the provisions that are in the building code around minimum levels of triggered retrofit acknowledge that it is difficult, or it's very there is a step function in terms of achieving what we call BPON, or new building equivalents, for retrofitted buildings, and the building codes in terms of setting minimum requirements do acknowledge that by permitting retrofits to achieve what's called the BPOE, or basic performance objective, for existing buildings, which is a more relaxed threshold as a minimum standard. But we like to explain to our clients, certainly in our practice, you have a choice. The minimum requirement from the building code is to achieve the BPOE, or perhaps a lower level of retrofit if there's a retrofit ordinance that only requires you to go to this level. But you need to be aware that for non-structural performance, or for certain elevated levels of shaking, your building will continue to perform. It won't perform as well as the equivalent new building. And at this, particularly early in the design, those are some decisions that need to be made. It's hard to change those halfway through the design process, and helping your client understand what the implications are from a construction cost standpoint, schedule standpoint, architectural impacts are important to have everyone understanding from the get-go. But it's certainly possible to achieve. And ASC 41 has a process that allows you to target what's called the BPON for existing construction retrofits.
Gotcha. Thank you.
Gustav, you're next.
Yeah, thank you for the presentation. I want to know that in buildings where the first mode of vibration is torsional, so do we need to do pushover analysis? Because generally the first mode, if it is translational, then we generally do the pushover analysis, because it is at par with the, we can determine the capacity of the building with pushover. So I want to know, is it possible for a building who has the first mode as torsional, do we need to do pushover, or we do time history analysis for that?
I think if you're stepping through, I guess my quick answer to that would be it's probably not appropriate to do a pushover analysis. If you step through the detailed provisions and say ASC 41, you'd probably find that the building wouldn't be permitted to be evaluated using the pushover analysis method for the reasons you've talked about, torsional response and other irregularities in terms of, or the quantitative measures of torsional irregularity that are in the standard as well would probably preclude you from using a pushover analysis, and you would end up going to a nonlinear dynamic analysis. I think certainly in our practice, we find that the pushover analysis method is too restrictive and it has too many assumptions built into it. And for most complex real buildings, there are too many issues with strength degradation and incorporating brittle materials and the response of some of the non-conforming components and the torsional regularity issues as well that you've touched on, that just make it too hard to try to apply a pushover analysis. You're better off to, our computers have got so much better over the last 10, 15 years in our ability to analyze structures quickly using time history analysis. It's kind of it's almost a no-brainer to go to a nonlinear time history analysis in most cases.
Okay, sir. And sir, I need one more. I have one more query.
Sure.
Generally, when we take the drift or displacement, what do we take generally in pushover analysis? Like, is it the maximum interstory drift ratio or the roof drift ratio? What do we generally take in the x-axis, like for the pushover?
Well, there's a target displacement that's defined in, say, ASC 41. So Chapter 7 describes how to determine a target displacement, which is not necessarily at the roof, but it sometimes can be. And then that's what you calibrate your pushover analysis to determine the performance point. But if you're evaluating deformation compatibility with secondary elements or things that aren't explicitly modeled, you may end up having to go and interrogate your results at that target displacement to extract, say, interstory drift ratios at critical locations or all locations over the building, to then apply those drift ratios to look at the implications for the secondary components.
Okay, sir. Thank you, sir.
Other questions? I've got one while people are thinking.
Sure.
I'm curious, what percentage of your work is retrofit of old structures versus incorporating some of these seismic designs into new structures?
Probably about, I would say about a third of our work is retrofit of complex existing buildings and historic preservation. We have a smaller percentage of our new construction work that is purely performance-based. And I think we're increasingly seeing it in higher seismic areas where the code provisions around, or the code provisions, building code provisions and limitations, and some of the high seismic hazard definitions are becoming more and more onerous, and it's advantageous to spend the time to do the more advanced analysis, to work with an engineering seismologist to understand the seismic hazards at your site, to step through that more detailed analysis, or the more detailed performance-based approach for new construction as well. And that's maybe, I don't know, 10% of our projects are going down a performance-based approach for new construction. And then even on top of that, we do use performance-based methods like this to at least do some validation as well. To one side, we'll present and develop a conforming design to the code, but we also want to make sure we understand some of the unique characteristics of a component or of a aspect of the structural response that needs to be, we want to have some additional validation so that we can go step confidently through the detailed design of a collector, for example, by doing a nonlinear analysis to supplement our understanding of how the building's going to respond from a code conforming standpoint.
Sure. Thanks. It's interesting. All right. Any last quick questions? We're just about at 3. So I think that's about it for now. So Bill, thank you again. This was really fantastic. And I hope everyone can join me in giving him a virtual round of applause for that great talk. And I think Ahmed just wants to pull up his screen one more time and give a brief last reminder of our upcoming workshop. If you liked this one, we promise you'll like the next one.
Yeah, thank you so much, Bill, for the webinar. I would like to remind everyone of our next workshop on Monday, April 19th. It's going to be as good as this webinar is. We have more information for you guys waiting at our platforms and social media. And also you can find the registration link for registration for the webinar. It's going to be very informative and beneficial for everyone to attend. As I told you, some of you will be graduating this year, and you guys want to know more about how to stay connected with EERI after graduation. And we're already looking forward to seeing you there as well. Thank you for today, and have a great rest of your time.
Thank you, everyone.
Thanks again, Bill.
Welcome.